A capacitor stores electric charge. It doesn't allow direct current to flow through, and it behaves as if alternating current does flow through. In its simplest form, it consists of two parallel metal plates separated by an insulator called the dielectric. The capacitance of a capacitor measures its ability to store charge and is stated in farads. The capacitance depends on the area of the plates, the separation of the plates, and the material of the dielectric. When choosing a capacitor, besides the value, the tolerance and the stability, there are two additional factors which should be considered. The first one is the working voltage. This is the largest voltage which can be applied across the capacitor and is often marked on it. If it's exceeded, the dielectric breaks down. The second one is the leakage current. No dielectric is a perfect insulator, but the loss of charge through it as leakage current should be small. A capacitor can be charged by connecting a battery across it. If the positive terminal of the battery is placed upwards, positive charge accumulates on the upper plate of the capacitor, while electron accumulates on the lower plate. Using the equation shown, you can find out the charge stored by a capacitor. A capacitor stores the electrical energy it received from whatever charged it. It can be shown that the energy in joules stored by a capacitor is given by the equation shown. When capacitors are connected in series, their equivalent capacitance can be defined by the equation shown. Furthermore, when capacitors are connected in parallel, their capacitances add up. All electrical or electronic circuits or systems suffered from some form of time delay between its input and output, when a signal or voltage, either direct or alternating current, is firstly applied to it. This delay is generally known as the time delay or time constant of the circuit, and it is the time response of the circuit when a step voltage or signal is firstly applied. If you set up the circuits shown and plot graphs of current against time, and voltage across the capacitor against time from the readings, you can see that the current has its maximum value at the start when the capacitor begins to charge, and then decreases until it becomes zero. While the voltage across the capacitor rises rapidly from zero and slowly approaches its maximum value, which it reaches when the capacitor is fully charged and the current is 0 ampere. A time constant is a useful measure of how long it takes a capacitor to charge through a capacitor if the charging current is remained steady. As seen from the graphs, if the current does not remain steady but decreases gradually, the time constant can mean the time it takes to charge 2/3 of the charging voltage remaining at the start of the time. The time constant is the product of the capacitance of the capacitor and the resistance of the circuit. The equation is created from various substitutions shown. Capacitive reactance is the measure of the opposition to alternating current. Its symbol is Xc and is measured in ohms. A capacitor offers less opposition to alternating current when its capacitance is large, and the frequency of the alternating current is high. The capacitive reactance can be defined by the equation shown. When alternating current flows through a resistor, the voltage and current are in phase. However, when it flows through a capacitor, the current and the voltage are out of phase by 1/4 of a cycle, with the current ahead. Different parts of an electronic circuit are often coupled by a capacitor and a resistor. In this section we will work out what effect the time constant of the coupling circuit has on the waveform of the input. Square waves will be considered as the test waveform since they contain many frequencies. When square waves are pulsed into the circuit, the voltage across the resistor is measured. If the time constant is much smaller than the period of the square waves, then the waveform of the voltage across the resistor will be a spiky one as shown. If the time constant is much greater than the period of the square waves, then the waveform of the voltage across the resistor will be a different one. If we pulse square waves into the circuit, and measure the voltage across the resistor, you can see the waveform varies. If the time constant is much smaller than the period of the square waves, the waveform changes entirely. The green line is the input while the red line is the output. If the time constant is much greater than the period, the waveform changes as shown, like a normal sine wave. Subscribe to our channel. and press the link below to like our Facebook page, Perpetual Magnetic Motor Development. See you on the next episode.